All right, everybody, we are going to get started here. Welcome to the last regular class for combinatorics for the semester. Try not to look too happy about that. It's a little bit bittersweet, I'm supposing, at least for me it is. It's been really a great semester. I've really enjoyed getting to teach this class again. We had our resident combinatorialist retire a couple years ago, and I've been getting the benefits of that ever since, getting to teach the class over and over again in his place. So just a couple of quick reminders. First of all, don't forget that I am going to be doing a review session for our final exam. The review session is going to be on Sunday, starting at noon. So 12 noon, and we're going to go till about 2:30. I have to stop and give myself a little bit of a break because I'm going to do another review for my other students at 4 o'clock. So we'll go for maybe 2.5 hours, something like that. And we'll do this in this room, so here. And my plan for the review is to really just throw a bunch of practice problems at you. And I might jump all over the place looking at topics. And of course, I'll answer questions if there's certain things you would like me to sort of spell out again or go over again. We certainly can do that on Sunday. I think that'll work out fine. I also have a ton of office hours officially starting Sunday night and then going into Monday and then also on Tuesday. I actually will probably be around also tomorrow and Saturday. I'm almost always, whenever I'm in my office, I'm amenable to talking to anybody about anything. So feel free to stop by. If you really don't want to make the trip down to campus, but you've got a question, you can also shoot me an email. We can jump into Zoom, whatever. Pretty much for the next 7 days, I guess 5 days for this class. I'm mostly just trying to get everybody ready for their final. So I want everybody to do well. I hope it'll be a good preparation for next week. Our final, just to put a dot on the I and cross my T on this, just to make sure everybody knows, it is on Tuesday. And it is from 5 to 7 p.m. And that is also here in this room. And don't be surprised if I give you a little bit of extra time at the end. If anybody has an issue with that, like if you have another final right at 7, maybe you want to let me know that just so I kind of have a heads up about it. I'm hoping that most of you won't be under that kind of pressure because I hate to have you being rushed out the door or anything. I'm obviously going to write something that should be doable within this time frame, even with the proofs that you would be writing. So if some of you don't want to do those proofs ahead of time, that's okay. It should still fit within this time frame. However, I do know some of you are interested in kind of doing those proofs in advance. So Sunday and Monday, I have those official office hours. If you check with me ahead of time on a Saturday time frame, that's also possible. Probably not Saturday morning, but later in the day on Saturday, I might be around as well if people want to get that kind of squared away.
Did you say that some of us could like maybe Zoom in?
Yeah, I'd like you to let me know if you want to do that. Just have a one-on-one with me about that and we'll figure out what would be the best way to handle that. Okay. Yeah, that's also possible. If you don't want to come all the way down to campus, but you'd like to get the proofs done early. Everybody knows what I'm talking about, right? There's a list of theorems, 4 theorems. I'm going to choose 3 of them to put on your exam, of which you will then choose 2 of those 3. So that's kind of the game plan for that. Okay, so yeah, and I went over the resources folder on Tuesday, I think. And of course you have resources folders for both midterms as well. So everybody's got like 2 of every exam to go back to and review, lots of practice problems. And heck, you guys can make up your own problems. This is combinatorics. An 8-year-old can come up with these questions. So I'm pretty sure you guys can too, right? So make up questions, quiz each other, draw graphs and ask people questions about them, make up combinatorial arrangements of things and ask people questions about them. It's not that hard to do. And it's pretty much how I'm going to write my exam is by that same strategy. So that's pretty much going to be it. As for today, we're not, I was about to say we're not going to be reviewing in class today, but then I remember the professor who I had as a student, and he came in the first day of the semester. He said, "Okay, we're going to start reviewing for your final now." And it was like the whole semester we were just reviewing for the final. I guess that's one way to look at it. But no, I'm actually going to talk about a few more things regarding colorings of graphs. And then I've got some group work for us to all practice it together. You also have a homework assignment. By the way, I fixed the link now. You can actually submit the assignment. So that should be good to go. Thank you, Nikolai, for that. And so I think we're in good shape. That's due on Sunday. So my plan is to get those graded by Monday, and we'll have your whole grade figured out, except for the final, basically, at that point. So that's kind of where we stand. Does anybody have any questions? Nikolai? If it's during my office hours, you don't have to tell me ahead of time. You just show up anytime during those office hours. If you want to come in at some random time, then you're taking a chance. If you don't communicate with me, you're taking a chance that I won't have disappeared for 3 hours or something. So you would be best off to either come during my office hours or send me an email and say, hey, could I come in? I can't come during your office hours, but could I come in at X time? And that would also work. Yeah. Okay. Anything else for now? Everybody stoked? Ready to bring your A game on Tuesday for the final? I hope. Hopefully, yes. Get ready. I want everybody to do well. You got it. I'm going to Hawaii next week. And I do not want to be in a bad mood when I go to Hawaii. So you guys have to help me out. Get me in a good mood before I head off.
What do you?
I'm leaving actually on Thursday. So I'm going to be grading like crazy to get things done before I go. But we'll see how I do with that. It might not be so easy. Anyhow, yeah, I have to come up with some kind of question about Hawaii. I'll think about it. Anyway, so let's see. Yeah, let's just remember what we were doing last time in class here. We're talking about trying to color some geometric figure. And so I'm calling that omega. And I put most of this is just notations on the board here. So if I want to collect all of the possible colorings of the vertices of the figure, that's just script C. And so notationally, C could be thought of as a vector, right? You have the color of each of the vertices. So that would be N data points that could be listed as a row vector, so to speak. And so C is just some coloring of the figure, right? And then in addition to the colorings of the figure, it's also important for us to be thinking about the symmetries of that same figure. So how can we take the figure, the object or whatever it is, pick it up, twirl it around, and set it back down on top of its same position, but perhaps not with the same vertices in the same spots, right? So you can take a square. We did the square on Tuesday. You can rotate it. You can reflect it. Right? And there's 8 different symmetries of that square. And that forms this group G. G is a group here of the symmetries of that figure. Right. Okay, so with each figure, we can associate the colorings and the group. Of course, colorings also depends on how many colors you're going to allow yourself to use. So that obviously is part of what goes into this, but it doesn't really need to be in the foreground here. What we are most interested in doing is counting the non-equivalent colorings of a figure. So we don't necessarily want to draw all possible colorings, just the non-equivalent ones. And to help us with that, I just want to remind you what it means for 2 colorings to actually be equivalent. Remember, if they're equivalent, it doesn't mean they're the same, but it means I can obtain one from the other by just performing one of my symmetries. So there exists a symmetry F in my group, such that when I apply F onto one of my colorings, it brings me to my other coloring. So that's basically what it means for 2 colorings to be equivalent. And then finally, a couple more notations down here. We talked on Tuesday about the stabilizer of a coloring. That's G of C. So here we have a particular coloring in mind, and we're looking at all of the symmetries that literally leave that coloring the same. So F star C equals C. And this is called the stabilizer of C. So for any coloring, there will be a stabilizer for that coloring. And of course, it could change from one coloring to the next. these all form subgroups. I think in the Brualdi's book, he just says that it forms a group of permutations. I think it would have been better to just say it forms a subgroup of G. It consists of some of the symmetries of the figure, okay? So that's one perspective. You fix a coloring and look at all of the symmetries that do nothing to that coloring. That's the stabilizer, right? And those always form subgroups of G. The size of any stabilizer has to divide the size of your group of symmetries by Lagrange's theorem from group theory. So there's a nice result about the size of the stabilizer. So if your group of symmetries has 8 elements in it, then your stabilizers all have to have size 1, 2, 4, or 8. That's it. You don't have any other choices. Now we can turn this perspective on its head, and instead of starting with a coloring and asking which symmetries would fix that coloring, we can instead start with a symmetry and ask which colorings would be fixed by it, right? So it's the same equation, F star C equals C, but here what we're doing is we're fixing the symmetry, and then we're looking at which colorings would have been fixed by that. And this turns out, well, 2 things. It doesn't have a name. I'm sorry. I looked again in the book. I'm like, surely he's got a name for this. He doesn't. So this is the stabilizer. This is just C of F. Okay. It's just the best I can come up with. And the second thing is that this one is actually going to be the more important one. C of F is going to be the important one for the Burnside theorem, which is the theorem, the big theorem that counts the non-equivalent colorings of the figure. So yeah, so both of these though are very important concepts, and it's worth understanding them in detail. So are there any questions so far here, what we've said? This is just recapping from Tuesday. I just wanted to kind of get the notation back on the board again before we actually get into the results here. So far, are we doing okay? Yeah, Khalil?
For the stabilizer?
Yeah. Yeah.
See what transformation.
They'll give you exactly the same coloring back. Yeah. Yeah, that's the definition of the stabilizer. Yeah, and it forms a subgroup of the group of symmetries.
And
Yeah.
you would have to be given like what the C is.
Yeah. For the stabilizer, it has to be the stabilizer of a coloring. And for the C of F, you have to be told what F is in order for that one to make sense. Yeah, absolutely. So these are things that you could calculate. I mean, I could give you a problem on the test. I could say, here's my geometric figure. I can color it for you ahead of time, and then I can say, all right, write down what all the symmetries are that are fixed by, that fix that color. And in other words, write down the stabilizer. Yeah, that would be a reasonable sort of standard test question that I could ask. So, okay, any other issues so far? Get myself set up here. So we got a lot of people in Zoom today. I'm gonna try to make this a decent recording. Okay, so there's basically just a couple of theorems leading into Burnside's theorem, and then we're gonna give the proof of Burnside's theorem. So let me come back to this. I think I have talked about a little bit of this already, but I don't mind just putting it down in the notes one more time here, guys. Theorem 14.2.1. What this says is let C be a coloring, so it's in this script C set. It's a coloring of omega. And let F and G, little f and little g, be in the group of symmetries. Okay, so then we can ask ourselves, under what circumstance would F star C be equal to G star C? Okay, so this is what the first theorem is going to be about here, is that we'd like to know, well, under what situations would the two different symmetries, potentially different symmetries, end up affecting the coloring in the same way and giving me this. This is just another coloring of omega, and this is just another coloring of omega, and I'm just saying that they're equal here. Well, it turns out to be if and only if the inverse of F composed with G. right? If this is in the stabilizer of the coloring C. This is the result. And the proof of this is really pretty short. I'll just jot it down briefly for you here. So first of all, for the forward direction, this is an if and only if, so I do have to go both ways here. For the forwards direction, if I just start with, so if I assume that F star C is equal to G star C, then what I can do is apply F inverse on both sides, right? So then I can apply F inverse to both sides of this equation. So F star of F of C is equal, sorry, F inverse star F of C is equal to F inverse star G star C. Like so. And the way we evaluate these stars in succession is literally to turn these into compositions. So we just have F inverse star F applied to C on the left. F inverse is composed with F, sorry, it's F inverse composed with F, and that is applied to C. And on the right-hand side, it's F inverse composed with G being applied to C. But of course, what is F inverse composed with F? The identity permutation, which when you apply it to a coloring would just leave that coloring the same. So C is equal to F inverse composed with G applied to C. And that literally just means that F inverse composed with G is in the stabilizer of C, right? So F inverse composed with G is in the stabilizer of C. So we certainly have that much already clear. The reverse direction is also very quick and sort of no surprises at all. So it's mostly just reversing the steps that we've already written down, right? I almost don't need to do it, but I'll start it off here. Let's assume that F inverse composed with G is in the stabilizer of C. Just up a little bit closer. So this just means that when we apply F inverse composed with G to C, we just get C again. And that's just F inverse star G star C, still equal to C. Okay, and now we're just going to apply F to both sides. Right. So apply F to both sides, so then we get F star, F inverse star G star C equals F star C. And this part just becomes the identity element again. And so we just get G star C equals F star C. Right. So nothing too surprising here with this particular result. You might notice that if we were to just take F to be the identity symmetry, then of course F inverse is also the identity symmetry. So if we could just kind of ignore the F for a minute, you see that what's left on the statement is really just the definition of the stabilizer again, right? So if I get rid of the F, now I'm saying G star C equals C, right? If and only if G is in the stabilizer of C. Totally reasonable. Now you can almost think of this as just a generalization of the definition of the stabilizer, right? As literally what it is. So this is kind of a nice result here. Okay, so I want to make a quick note here about what this theorem allows us to say that I hope will make some sense. I'm going to just put it here, I think. Nice amount of room to work with right now. If we fix the G, so for fixed, if we fix the F in the group of symmetries, I'm going to imagine for a minute that I have fixed the F. So F is already fixed. And I want to ask, how many different G's could I now pick in this theorem, little g's, So with the little f already fixed, how many little g's could I find such that f star c would be equal to g star c? Like, how many of these little g's would there be? Given that the f is fixed here. So the question is, how many things can you compose with f inverse so that you'll get something inside of the stabilizer? Let's say that the stabilizer has 10 elements in it. Let's say this is 10 things here. And f inverse is fixed. How many different g's could you come up with such that the f star g would be within that list of 10 things? Kristen?
Would it be thinking no more than?
Oh, you're thinking too hard. You're thinking too hard. So I already know what f inverse is. I'm trying to put something in this box, and I've got 10 different elements in this stabilizer here, right? So I want f inverse star whatever to either equal sigma 1 or sigma 2 or sigma 3. How many ways could I fill in that box? Just one? I think it's gonna be 10. I think it's gonna be 10 because see, if I know what this, guys, if I have f inverse star something is equal to one of 10 different things, I can solve for that question mark in 10 ways. All I have to do is take whichever of these 10 things I want, left multiply it by f, and that tells me what to put in the box. Right? So where's the 10? So if I had a stabilizer with 10 things in it, that would mean there would be 10 different ways to fill in this box to make this equation legit. In other words, it's the size of the stabilizer. That's how many g's there are. Let's write that down. That's my note. There are, just make sure everybody's able to see this okay. Coming over here to this other board. Right. There are size of the stabilizer of G choices for the little g in G such that f inverse composed with G lands in the stabilizer of C. So there are this many symmetries that would have the same effect on C as F does. Right? See, you start with this coloring C, right? And you can imagine applying every single symmetry of the group to it. But that's not going to give you a different coloring for each of those symmetries. Some of them are going to be repeating themselves. Anytime you pick a G, right, such that F inverse composed with G is in the stabilizer of C, you're not going to get a different coloring than you had already gotten when you applied F. Right? So I'm just trying to say, like, how many different results can you have for F star C, right? So the question is sort of like, what is the size of this set? Right? If we started with a coloring, and we said, let's hit it with every possible symmetry, right? How big is this set? That's really the question that I'm trying to get at. And we're actually going to state it now as a corollary of this first theorem. Okay? Is everybody with me? Does that seem reasonable? Okay, let's write down this corollary then. Corollary, I think it's 14.2.2. And here is what it says. So again, we're going to let C, the vector C, be a coloring. So C is in the script C again, just like before. Okay, and then the number of different colorings that are equivalent to the coloring C itself, equivalent to it, is how many are equivalent. Ultimately, I want to know how many non-equivalent colorings of the figure are there. But to get to that issue, we need to answer this question first. how many colorings are equivalent to C, right? Well, then simply by notation, the answer to that is, well, we take all possible symmetries of the group and apply them to our coloring. So I'm gonna take my coloring, everything in this set is equivalent to C. What does it mean to be equivalent to C? Two colors are equivalent if one of them is just F star another one. So anything that is of the form F star C is equivalent to C, right? So everything in this set is equivalent to C. The question is, how big is that set? It's not as big as the size of G. It looks like it is, because for every F in G, we're going to have an F star C. It looks like that's going to be as many elements as there are symmetries of the group. But we know better than that, don't we? Because we know that sometimes we get the same result. We can have two different symmetries that are giving us the same result, and that's where this number gets cut down. And so the correct answer to this question is not the size of G, which is what it kind of looks like it's going to be at first. It's not going to be that many. In fact, it's going to be this many. The size of G divided by the stabilizer of C. Okay, so the reasoning again is that, well, how many different F's will give me the same F star C? That's just however many different G's I could pick that would have the same result as F here, and the number of different G's was just the size of the stabilizer. If this stabilizer has 10 things in it, then there were 10 ways to fill in that box. You see? Nikolai? Yeah, we could certainly rework this equation around in that sense to find the size of G, but of course, usually the size of G is something we know. And so it would be kind of a backwards way of playing with the equation. Because generally the coloring is the thing that's kind of being pulled out of the sky, and all of a sudden you're like, oh, what is this? So I would say that it's generally going to be used more frequently in the form that I've expressed it right here. Okay, so there you go. All right, are we reasonably okay with that corollary? Yeah, Kristen?
Three red. We have 5 first heat, 3 red, 2 blue. Right, I'm thinking of the homework problem right now. Already. 3
Okay.
red.
Let's go back to our square from Tuesday where we had 3 reds and 1 blue vertex. And so we'll just make an example here. I think this is not a bad idea to stop for a second and do an example of this. So my coloring here, right? My coloring here would be, I don't know, we could think of it as red, 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 blue. If we've ordered our vertices sort of 1, 2, 3, and 4 like this. So we kind of put them in that order, then there's your coloring right there. And so the question might be, how many equivalent colorings are there? How many equivalent colorings to C are there? This is a reasonable little practice question with this corollary that we just did. So again, this symmetry group, as we know, is the dihedral group with 8 elements. So there are 8 different things I can apply to C right now. But that doesn't mean that the size of the set is 8. And in fact, I think we probably know the answer to this just from common sense thinking about it. How many different ways could you move these reds and blues around and get a different picture? How many different pictures would there be? I actually did it on Tuesday. Yeah, I mean, basically, you can move this blue corner to any of the 4 corners. So you would have, so the correct answer is 4, just by looking at it. Because you can have right? What are they? That obviously this coloring is equivalent to itself. But we can also rotate by 90 degrees and put the blue up here, everything else red. Or we can rotate by 180 degrees and put the blue in the upper right corner and all the rest are red. Or we could put the blue in the lower right corner. Okay, so all of these are equivalent to each other, right? They're basically the same necklace, right? So we wouldn't count this as 4 different necklaces. This is just one necklace. The blue bead can be anywhere. It doesn't really matter. So now how do we get 4 from the formula? Well, we just have to, so the solution from the corollary 14.2.2, we just have to take the size of G divided by the size of the stabilizer of that coloring. Right? The group is the dihedral group. There are 8 different symmetries, right? But then we have to think about the stabilizer of this coloring. Like out of those 8 symmetries, which of them would literally leave those 4 colors exactly where they are right now? Obviously, the identity element, right? Well, we know the answer is going to be 2. The other one is going to be, isn't it going to be this diagonal?
Yeah.
Right, which I think was, oh geez, tau something.
Tau two.
I'm gonna give you this table on your final, so you're not gonna have to, there's a handout in Canvas, I think I showed this to you the other day. This is tau 2. So this 2 is the identity and tau 2. Okay, so that's what you have. Yeah.
Is that like accepted, just how to is that sort of reflection, or can we just really like label it however?
You can kind of label it however you want. I don't care. I mean, probably gonna give you this, but see, I might not give you a square on the test. I might give you a hexagon. So in that case, we don't have the diagram, so you can just draw it and label it. I'm totally fine with that. Yeah.
So if you're giving us an n, like some type of n-gon, we can just assume that it's all equilateral, like, because like on
I'll
the,
say regular n-gon.
Okay, 'cause, like-
If I say regular, that means it's all the edges are the same size.
Okay.
Yeah, that would be a better way to say it. Yeah, for sure. Kristen. That's next. That's next. So see the idea now, if I want to count how many non-equivalent colorings there are, I have to first figure out how to lump together all the ones that are equivalent. So these 4 colorings, right, are only going to be one non-equivalent coloring relative to anything else we could have done to the necklace, right? Yes, that is exactly right. So now, my friends, I am ready to do the big theorem, Burnside's theorem. You ready? I
Yes.
love this thing. And if I love it, if I love something, you know where it's gonna show up. Problem for you guys is I love everything. There's nothing that I don't love. Okay, so let's see, this is gonna be theorem 14.2.3. And this one is the Burnside theorem. The last sort of big result that we're gonna have time for this semester. So here's what it says, the number, and this notation is n of G and C. So script the G for the group of symmetries, the C for the colorings. The number of non-equivalent, this is really what we care about, right? Colorings of omega is, and here's the formula, n of G, comma, C, sorry, is equal to, and I wrote it down briefly on Tuesday, but now we're gonna get the proof as well. We divide by the size of the group of symmetries, and in the numerator, we're going to do a summation this is a summation over F in the group G of the size of the C of F. Okay, so there's the formula. Okay, that is the formula. And one of the things I love about this theorem, aside from the fact that it's really a nice applied result, is I really, really like the proof of this. Okay, so I'm going to show you how this is proved, and then we'll maybe do a couple of examples, and then I'll let you do some group work and practice it yourself. What I'm going to do, guys, is I'm going to consider the set of all of these pairings of a symmetry with a coloring. So we take a symmetry F and a coloring C such that obviously F is in the group of symmetries, C is in the collection of colorings, and the other condition is that F star C is equal to C. Okay, so I'm going to, I have, what do I have in my hands? I have a bunch of colorings and I have a bunch of symmetries. I'm gonna create pairs of those. I'm gonna create pairs where I take a symmetry and I take a coloring, but I'm only gonna take those pairs where the symmetry fixes that coloring. So there'll be some pairs that I'm not gonna consider. I'm only considering this collection of them, and I'm going to count how big that set is in two different ways, thereby conducting a, what kind of a proof is that called? Combinatorial proof. Remember those? Yes. We're going to count how big this set is in two different ways. And I'm hoping you're gonna like how I do this. This is really neat. It's so exciting. I don't know what I'm gonna do with my Tuesdays and Thursdays after this. It won't be this exciting. Okay, so let me see. I'm going to do a combinatorial proof, and the way I'm gonna do this is I'm gonna do two methods.
Stop it.
Say again?
Like penguins.
Oh, penguins, you want penguins? Oh, geez.
Parking tickets.
Parking tickets, penguins,
Fire
fire trucks.
Penguins driving fire.
I'm gonna have fun writing this. I'm gonna have fun writing this final line. Okay. Here's the first method. Guys, I imagine you probably have a reasonable idea what I'm gonna do. I'm gonna count these pairs in two ways. One way is I'm going to fix what F is, and I'm gonna run through all of the C's that for that fixed F would have F star C equals C, and then I'm gonna sum them up over all of the F's. And then I'm just gonna reverse it. I'm going to fix the coloring, and I'm gonna run through all of the F's that make F star C equal to C for that fixed coloring, and then I'm gonna sum it up over all the colorings. You see, both ways are totally legit. You've sort of got two gears turning here. You have the symmetries slot, and you've got the colorings slot. You're gonna fix one of them and run the other one, right? And you do it in both directions, and it gives you two methods of doing it. I love it. Let's write it down. The first method is for each, blah, 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 blah. I get excited, I write too fast. For each F in the group G of symmetries, we count the number of colorings. Remember, this is one of the proofs that's on your list, so this is a good time to get good notes down. The number of colorings C, the vector C, fixed by F. By definition, we already have a concept for that, right? By definition, the number of colorings that is fixed by F is, remember the script C of F, the thing that doesn't have a nice name? Right? This is the set of colorings that are fixed by F. So for each fixed F, we count the number of colorings fixed by F, and of course we're taking the size of that set, so it's the number of such colorings. Okay, and then we sum over all F in the group. And this gives us the summation, where F is in the group of symmetries, of the size of C of F. So that gives us this numerator right here, exactly this numerator. Okay, so that's method number one. It's method number one. Method number two is just exactly the reversed situation. Method number two is just exactly the reversed situation, which is for each coloring. So this would be for each C in the collection of the colorings, right? We count the number of symmetries. So these are the little f's, the symmetries are the f's in the group G that fix the coloring C. So if we fix a coloring and then we ask, well, how many symmetries will fix that? Now that is exactly looking at the stabilizer of the coloring. And then of course, we're counting the size of that. How many things are in that stabilizer? How many F's are in that, excuse me, in that stabilizer? Okay, and then we sum. So I'm literally doing a parallel argument here. Does everybody see that? It's almost like what I did over there. I'm doing the same thing here. Then we sum over, this time we're summing over all colorings C in script C. And now I'm going to write down what that would be. So that would look like this. That would look like the summation of over C in script C of the size of the stabilizer of C. By the way, what do we want this to be equal to? On the left-hand side, we got this summation here, which is just the numerator only of my Burnside theorem. So I want that summation to come out to be this denominator times this number of non-equivalent colorings, right? This guy times this guy should equal the numerator. All right, so let's see if that's what it comes out to. Let's see if that's what it's going to come out to. So I'm going to actually have to do some work now on this side. We're going to have to do a little bit of work here. So this is a summation where C is a coloring. I mean, we already know that this does equal this. It's just not looking like my theorem yet, right? I'm just trying, now I'm going to do the algebra to show you that this summation makes up the product of the size of G and the number of non-equivalent colorings. So here's what I'm going to do, guys. I'm going to start by taking the size of this stabilizer and replacing it with some formula that involves the stabilizer already that we just came up with over here. We solved this for the stabilizer of C. Let's see. In the numerator, we're going to make a fraction. The numerator has the size of G on it. And then let's just check out what would we actually get in the denominator here. It would be, well, it's just the size of the set of F star C such that F is an element of G. So I'm just using the corollary in this first step here. This is corollary 14.2.2. Okay? Now the size of G, as you guys know, is a constant. And so it can actually be factored out of the summation. So my next step is going to be to pull the size of G out in front. And then I'm going to have that's times the summation. C is an element of my collection of colorings. And now we're left just simply with 1 divided by the size of the set of F star C such that F is in the group of symmetries. So just like that. Okay. So we're getting there because now I at least have the size of G. I'm ultimately hoping that this calculation is going to give me size of G times the number of non-equivalent colorings. I'm hoping that this summation part now is actually the number of non-equivalent colorings. That's what I'm hoping for. Right? Let's see if we can understand why that is. I'm gonna go ahead and do another equal sign. I think I'm gonna come up here so I have a little more room, move this a little closer for people. Okay, so I still have the size of G outside. I'm pretty happy with that at this point. And then I'm doing a summation where C is an element of my collection of colorings of 1 over, let's look at this denominator for a minute. This denominator is what? I start with C and I apply all possible symmetries to C. Doesn't that just give me all of the equivalent colorings to C? It's the number of colorings that are equivalent to C. Let's write that in words in this denominator. Can I do that? In the denominator, the number of colorings equivalent to C. These are equivalent. Those are the number of colorings equivalent to C. Now, let's imagine that there are 4 colorings that are equivalent to C. In fact, let's go back to this example. Let's say that this is C right here. Right? And there are 4 colorings equivalent to C, which would mean that in the formula right now, we would have a 1/4. Okay. But my question is going to be, how many times are we going to have that 1/4 showing up? Because this coloring produces a 1/4 in that summation, but this summation is over all colorings, including this one, and this one. So this coloring is eventually going to be one of the terms of that summation. And how many colorings are equivalent to this one? Or the same 4, right? So there's going to be a 1/4 coming from this guy. And then this coloring is also going to be one of the terms of that summation. And how many colorings are equivalent to it? 4. Which means I will get a 1/4 here. How many colorings are equivalent to this guy? 4. Is going to give me another 1/4. So I'm going to have 4 1/4s added together. Which adds up to 1. That adds up to 1, which is what we would want these 4 colorings to get lumped together as a 1 term, because it's going to be 1 non-equivalent coloring relative to the whole collection. Is not that beautiful? Is that not beautiful? Right? That I think is pretty sweet. So let's actually write a little explanation here, because this is the key point. This is the key point. If we group, so we'll add a little text here. If we group together all colorings equivalent to C. If we group together all colorings equivalent to C when performing this summation, if we group those together, I'm going to erase this to give myself a little more room. So if we group together all of the colorings that are equivalent to any one of them, let's just imagine we have a coloring in our hands and we group all of them together. We put these 4 terms right next to each other in the summation. Every coloring gets 1 term of that summation. We just put them all together back to back to back to back, right? Then what's going to happen is each equivalence class, these colorings form equivalence classes according to whether 2 of them are equivalent to each other or not under that definition that we started off with, contributes, I'm going to just write in quotes here, +1 to the total summation. I'm super glad, Christian, that you asked me to do this example, because it's really helpful Think about it, oh, it's 1/4 plus 1/4 plus 1/4 plus 1/4. I'll lump all those together, that's a +1. And that is one of our non-equivalent colorings. It's exactly what it is. And so what we get then, guys, I'm gonna come back to my equal sign here again, is the size of G times n of G comma script C. The number of non-equivalent colorings is what you're left with. You've represented each equivalence class exactly once. It adds +1 to the total summation, and the number of different equivalence classes is just a fancy math way of saying the number of non-equivalent colorings. That's right. That's right. So on Tuesday, we had 6, didn't we? With 2 colors, we had 6 different non-equivalent colorings of a square using 2 colors. And one of them is the one that's represented by this equivalence class. All of these are in one single equivalence class. Right? I can get from any one of these to any one of these by doing a symmetry. And that's what equivalent means. So yeah, you figure out the number of non-equivalent colorings by understanding how to lump together the equivalent ones. It's kind of an interesting argument. But these 2 methods counted the same thing. They counted the same thing, so therefore they must be equal, right? So let's just write a final sentence then to kind of wrap the proof together with a bow, and then I'm going to be happy with it. We'll do an example. Okay, since methods 1 and 2 yield the same count, you have to have the same amount in each case, then that means that the summation where f is an element of G of the size of script C of f must be equal to the size of G times n of G script C. And that is basically, that's your theorem. That's basically what you want. Okay. Nice. Is everybody okay with that? Christian?
Oh, if we were to write this proof.
Yeah.
We need to write that.
This needs to be included. This is a key point. I would want to see that. You could put it off on the side if you prefer, but it would need to be there in some form. You know, if you have a different way of phrasing it slightly, I'm okay with that, but this has to be explained. This is really the key step, right? Everything else this is mostly algebra going on here, plus that reference to this corollary. By the way, you're allowed to refer to a result outside of the scope of this result. So you could refer to this corollary. It'd probably be good to state it, but you would not need to prove the corollary also within the proof. Sometimes people ask me those kind of questions, which is a good point. Okay, let's do an example of the Burnside theorem, and then I'm going to turn you guys loose on some group. So far, so good? Jose?
You're about to, you're.
I'm just erasing everything you just want to ask me about. I'm really good at doing that.
You did it divided by the cardinality.
We didn't, yeah. So it is interesting that in this combinatorial proof, we rearranged the equation by moving the size of G over here. I mean, after all, we don't really want to have fractions to deal with, so it's better to have it phrased in this form. Yeah, absolutely. Okay, let's try an example here, guys. And this is, I know some of you have already done the homework, so I won't spend too long on this, but just to give you a quick little practice. So let's determine the number of non-equivalent colorings of a rectangle using P colors. So imagine that we have P colors that we can use here. So when I say a rectangle here, I don't want to think of it as a square. So I'll draw a rectangle here just to have a picture. And we have maybe 4 vertices here. I'll label those 1, 2, 3, and 4. So here's my rectangle, and I'm going to try to determine how many non-equivalent colorings could I make for this rectangle using P colors. So we're gonna use the Burnside theorem to figure this one out. The group of symmetries here, it might be helpful. What are the group of symmetries of a rectangle going to be? I'll do the easy one, which is the identity element. What else can we have? A 180-degree rotation. We cannot do a 90-degree rotation because 90 degrees does not set the rectangle back down on top of itself again. So I'll call that rho 4 squared. That's a 180-degree rotation. We used this notation on Tuesday, right?
Then the tau is vertical.
I can do the vertical and the horizontal tau, which are actually tau 3 and tau 4 in the notation. Again, I'm not going to be asking you to memorize which tau is which, so you don't need to get too stressed about that, but just so it's consistent with the handout that I did put together on Canvas, that would be tau 3 and tau 4. So my group has size 4. So by Burnside, the number of non-equivalent colorings of G, N of G comma C is going to be, we have a fraction here. The size of the group is obviously 4 on the bottom. And then in the numerator, we have to add up, well, I'm just gonna write them all out. So the C of the identity plus the size of C of rho 4 squared plus the size of C of tau 3 plus the size of C of tau 4. Be sure that you don't get too complacent about this. You know, it's easy to just say, oh, well, I'm doing it in my head and I'm gonna write down all the numbers. I think it's not a bad idea to kind of write these out so that I can see it.
Do you wanna see it written down like that with a fraction, or can we just list them out and then put them all together at the end?
You can list them all out and then put them together at the end. Yeah, that's fine if it's cleaner for you to do it that way. Do not mind. Okay, so let's work this out. Remember, each of these guys is counting how many colorings are being fixed by each of the symmetries. So the identity, it's always nice to start with the identity because it's kind of like a warm-up, right? For the identity, you're basically saying any coloring. Doesn't matter what you do, every coloring will be fixed by the identity. So you have P choices, P choices, P choices, and P choices. Remember, we're not using the old rules where you have to use different colors for adjacent vertices. So we will just say, in this case, P to the 4th. Okay, and that would be the first term. What about the 180-degree rotation? So now I'm going to pick a color. Let's say I pick red here. And then I'm looking for colorings that would be fixed by doing a 180-degree rotation. So if this is red, what else do you know?
3.
3 has to be red. Exactly. So I had P choices for that color, for that vertex, but then I had nothing to choose here. And then what about 2 and 4? Same choices. Maybe I pick yellow for vertex 2, then vertex 4 has to be yellow, right? So in that case, I just have P choices for both of those 2 vertices. So I would just get P2, sorry, P squared. Okay, what about tau 3 and tau 4? Pretty easy, isn't it, right? Just here's the vertical axis, right? The vertical axis would require that whatever colors are used on the left side would be matched by the ones on the right side, right? So that's, you only have 2 of the 4 vertices to choose freely. And then same thing for the horizontal axis, 2 more choices. So this would be the answer. We could leave it like that if we wanted, but I'll just clean it up just slightly as such. And then of course you could plug in P, whatever number you wanted to figure it out. I do want to point out that there can be sometimes a little bit of confusion about what symmetries are actually allowed. So let me give you an idea what I'm talking about. If we have a necklace, which is what you could think of here, I guess. If you have a necklace, you can rotate it and flip it around all you want, right? But what if I had a merry-go-round of horses in a circle? Maybe there's 4 horses in a circle and they're all facing forward. Each one is in front of the next one and they're going around. Obviously, you can take that merry-go-round and rotate it, right, as much as you want. But I wouldn't think flipping over the merry-go-round and having the horses upside down is going to go too well, right? So the group of symmetries for that physical problem would not make the same sense as for a necklace. right? So we would have only the rotational group, and it makes a difference, right? If we don't allow reflections, right, then the size of my group changes, the numerator changes and everything else. So if you have any questions about what's really allowed as rigid motions of your object, that's a reasonable thing to ask me about. I do have a merry-go-round on this group work. That's why I was thinking about it. But yeah, so something like that would be a little bit of an interesting situation.
You know that the cardinality.
True. Yeah, G as a group, it's definitely gonna always have at least one element in it. Other questions, Nikolai?
Well, I was talking with Fernando last week. This could be the last lecture.
Really?
Could be.
Oh, well, that's very nice of you. I feel a lot of pressure right now. Like I'm the last chance to make sure you guys are all on the straight and narrow going out from here, hopefully. Well, I am honored to be able to be a part of this. That's great. Awesome. Well, I tell you what, let's wrap up. We've got just a short bit of time, but I think you guys can probably do the Burnside's theorem pretty quickly now on a few examples here. A couple of them are word problems and a couple of them are actual pictures that you can work with. So let's do a little bit of group work, and please nobody leave early because I have to do something at the end of class also. So just hang tight, but I will make sure I save it. There's the group work, the 1, 2, 3, 4, 5, 6. And there should be markers everywhere. This is the last day for your group of partners, so. And Maddie, you're gonna have to join in the group. This is group work number 13. Kevin, do you have a group? You're gonna work with them? Okay.
DH, Kevin.
Come on down, guys. You know what? Oh, yeah, sorry. Sorry. Or do we need more? It was just you. All right, great. Yeah, you're welcome. Group work number 13. Kevin, sorry, could you work over here maybe? Because I just want to save the theorem in case anybody needs to look at it. Thank you so much. Come on down. Guys, please use the whiteboards. Let's use the whiteboards, please. I'll come around and help. Oh, here, let me erase. I'll close it. Huh?
I never look at any of this. Merry-go-round? It's crazy. That's good.
I'm working with Kevin, Kevin.
Why don't you guys get together? We only got like 5 minutes to do all these problems. 10? Okay, you say so.
Unless you wanna kick us out early.
Yeah. Yeah, I'll probably put up with you for an extra 5 minutes.
Did you get one for him?
I did, yeah.
We got an extra one?
Yeah.
You guys wanna work maybe back?
Yeah.
Yeah, that'd be great. Who are you working with, Khalil? Yeah, we could do it this way too. Yeah, the 4 of you wanna work together, does that work? And you can use some of that work, but you guys want to keep it longer. Thank you.
That's for question 1.
So this group seems to be moving along nicely. Let's get some, well, there's a lot of people in Zoom right now, so. I don't really think translations are gonna.
That's how. And that many, if we split something down here, that's the. Yeah. That would be the word.
Can we do translation?
Watch the Mary.
Oh, you're
right?
We can do rotation. It's not like an object, you know, you to understand the balance of the. So you get your rotation.
All of these are maps.
But like, on a three-dimensional object, the reflection would be like if you were on the side.
These are.
Right side to mirror the left side, I think. The way coordinates, the one in the middle wouldn't change, but you could mirror the other two. And one here, excited.
So what would that, if you were. What? Awesome.
And these color rings are there.
His argument with the squares is like, it's like.
You can pick it up and
You can pick it up and. Pick it up and flip, mirror it over.
Yes. Oh, yeah, okay. You're right. Yeah, I agree. There's three options for one. Yeah. There's three. Okay, then one rotation, one more, well. Yeah.
Yeah, so three arms you made for this one.
Right, right, there's, you know, color one.
If you wanna.
I won't.
This color. So you can down. But then. So yeah, so basically the, you only think about what color.
So, saying that you're rotating.
Basically.
So that's what. So yeah.
Oh, it all has to be the same color.
Anybody so?
If I only have 3 hours.
Because you guys, well, you told this way, this is. I really have one choice.
Yeah. And that's why each of these are.
This has to be on. Oh, yeah. That's what I got. But you see how you have to. So 7 we're not slipping, sitting home.
Right.
It's the original position, which is.
Yeah. Exactly.
So that.
All right.
So that's what they were saying.
That's what they're trying, if I have like.
And what's the one?
Yeah, let's actually.
Like say the merry-go-round, you wouldn't be able to use reflections, right?
Right, that's a physical limitation. We can't actually flip the thing over. Yeah. But you can rotate it. It's a rotatable object, but it's not a flippable object like a necklace ring. So that's where I was saying it might require a little bit of like an interpretation to kind of understand, well, what symmetries are allowed for that figure. Right? So for a merry-go-round, all that does is spins in a circle. It does not flip. Whereas a necklace could flip. So if I asked you how many necklaces there would be here, it wouldn't be the same answer. You'd have a group of symmetries twice as big, and you'd have that many more new terms in the numerator as well. Yeah, of course. So you remember guys there and all this, so you're gonna be totally good. I'm gonna probably put everybody in front staff. Whatever you want. Give me just a second. Hey, guys. I never like to keep people late. I've never done that. So, it never happens. I've only got like 2 minutes left, and so we're just about out of time here. But first of all, I just want to say thank you all so much for taking this class, because I really do love this material and teaching it, and I don't get to do that if people don't sign up. So I really am stoked about that. I hope that you'll keep in touch with, like, check these solutions to the group work, come to my review session if you can. But I have one last thing I would like to do today, which I have done every year except during COVID, but every other year since I became a professor, which is I love to have a picture of everybody who was in my class. And it sounds like this is a lot of people's last class, so I'll send it out to everybody and have a nice memento for the semester. But could I get everybody kind of up in front? We've got some beautiful pictures on the board. We've got this wonderful mirror. And I've got Ashley here who's gonna help me take a picture, 'cause I want to be in the picture too. You have to remember that as well. This is very simple, just. Submit her out. Honestly, and then. This is here. So please sit down. I'm just trying to make this sign. Do you want to sit in a chair? Jim? No, that would be. How's it looking? Is it looking?
Yes. It isn't like an. Yeah. Okay. Gotta move into it.
Sit in that chair. Yeah, that would be great. I'd like to stand maybe in the back over here. And we're just gonna get a quick class picture. You guys have to actually pretend like you're having a good time in this class. Just smile a little bit. And Ashley, let us know. Take like 3 or 4. Stop it, guys. Yes. Thank you.
Okay, I think I got it.
All right, thank you.
That's a great question.
I appreciate that. All right, guys, yeah. Just check the solutions online and then ask me questions if you have any.
Thank you, Ashley.
Thank you. And I'll be downstairs if anybody's got any questions. I've got office hours tonight, so be glad to help out. And that is a wrap.